I have a file here in which I already have some of the data that's inputted, and we'll be able to see in here what the software is actually going to be doing. So in this case, I asked the software to generate 5,000 different designs. We can review the progress bar at the bottom to see that we've done about 20% of that in a very short amount of time. So each of the parameters that you see in the table below is going to be inputted as a minimum value and a maximum value. These two values can be the same, as it is the case here, in which situation the software is just going to consider that this is a fixed value. If the values are going to be different, like it's the case here for the rotational speed, hub diameter, number of stages, etc., the software is going to pick a random value between the mean and the max and generate a design based on this value. It's going to do this for each parameter, in this case 5,000 different times. As this is going, we can see on the right side we have a 3D design space on which we're going to be able to review all the different geometries that have been generated. So here we can see we have finished the calculation process, and out of the 5,000 designs generated, there's 247 that can be reviewed by the user. The other ones just don't fit the constraints specified in here. So each of these dots is going to be corresponding to a different design. So here we can see one of the actual turbine that was generated and which correspond to this dot right here. If I select one right here, we're going to see this is going to update to show us the flow path corresponding to this geometry. If I select another one down here, we'll see again this is going to be a different geometry altogether. So the goal of this module really is going to be, this preliminary design module is going to be to figure out what is going to be the best combination of input that's going to give us the best output, so that we can select the best design for our particular application based on if we want to improve or increase the efficiency, if we have certain size restrictions, manufacturing limits, etc. So instead of clicking on all of these dots manually and seeing which one we like and which one we don't, we have this Design Space Explorer tool, which can be very, very useful. It includes two different tables, one right here and one over here, which will be used to plot whatever parameter we want on each of the various axes, as well as the color of the dot. So for example, I can plot the number of stages here on the x-axis, keep the power on the y-axis, and I can see that for a one stage and two stage machine, there was no design that was fitting these conditions. For a three-stage machine, I can get up to 12.5 megawatt of power. With two-stage machine, no one-stage design here. With a three-stage machine, I can get up to like 13.2, etc. Alternatively, I could, for example, look at the efficiency. For example, here, if a two-stage machine is going to provide an efficiency way too low, we can say the minimum number of stages we want to consider is going to be 3, in which case you can see it grades out some other points here that are not going to be applicable. If I can get the same efficiency for a 6 and a 10-stage machine, there's probably no point in going with a 10-stage machine. That's just an example here. So I'm going to set it, for example, to 8 for the maximum value. In the same way, I can look at the influence of the rotational speed and see that here around 4,500 RPM is where we're going to have the best performances. Same thing for the hub diameter, etc. So by looking at all of this, we can very easily and very quickly figure out what is going to be the performance of the machine at the 1D level, as well as the overall size and configuration of the machine.